In section 2, we're going to go ahead and talk about performing a significance test for a mean. So just like with a confidence interval, you have to determine whether or not you're going to be doing a t interval or a z interval. You have to do the same thing with a significance test. Are you going to do a z test or a t test? So it works the same way as a confidence interval. Use a z test when you know the population standard deviation, which we use sigma for, and you do a t test when you know the sample standard deviation, which is S sub x. So the first thing that you want to do is write your hypotheses, figure out your critical value based on your level of significance. So for our hypotheses, our null hypothesis will always be that mu equals mu naught. So just like with proportions, we had P equals P naught, we have the same thing for our null hypothesis for means. It's always going to be equal to. Our alternative hypothesis is we then have three choices. We have that mu can be greater than mu naught, mu can be less than mu naught, or we can have that mu does not equal mu naught. So exact same thing for our null and alternative hypotheses, either greater than, less than, or does not equal. Once you have those done, your second step is then to check your three conditions. So random, do you have random assignment, which happens for an experiment? Or do you have random sampling, an SRS? You check independent. So if it's an experiment, remember, we go ahead and assume independence because one data point doesn't affect the next. But if you're doing sampling, you have to check your 10% condition, which is n is less than or equal to 0.1 of our population. And then lastly, normal. So if your sample size is greater than or equal to 30, you can go ahead and assume it's normal. If it's not, then you either have to be told the population or sample appears to be normal, or you can graph the data to make sure it appears approximately normal. And then for our test statistic, so just to kind of refresh what our test statistic is in general, it is the statistic minus the parameter over your standard deviation. So we have two different test statistics depending on whether or not you're doing a z-test or a t-test. So if you're doing a z-test, we have z equals, and it's x bar minus your mu naught over the population standard deviation over the square root of n. So we use normal CDF to find our p-value once we have our z-test statistic. Our t-test statistic is going to be t equals, numerator's the same, it's still x bar minus mu naught, but our denominator is now s sub x over the square root of n. So we use something called t-CDF to find our p-value. Still find it by going to second vars, and then t-CDF will be listed instead of normal as well. And then for our sentence, you decide whether or not you reject or fail to reject the exact same way we did for a proportion. So if our p-value, I don't have enough space to write it, so if the p-value is greater than alpha, we fail to reject our null hypothesis. And if the p-value is less than alpha, we reject our null hypothesis. So that step is the same. And then after we decide whether or not we we don't need to have anything there because it's whatever your p-value is, and it's bigger or smaller than the significance level, you either reject or fail to reject. And then we do not have, or we do have enough evidence that the mean, and then whatever the rest of your problem is in context. Very similar to proportions. So let's go ahead and do some examples. So for our first example, we have that a company claimed to have developed a new AAA battery that lasts longer than its regular AAA batteries. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. An SRS of 30 new batteries lasted an average of 33.9 hours with a standard deviation of 9.8 hours. Do these data give convincing evidence that the new batteries last longer than average? Use a significance level of 1%. So first thing I'm going to decide, am I doing a t-test or a z-test? So we found that in our SRS, we had a standard deviation of 9.8. So that tells me I'm doing a t-test. So we're doing a t-test. So null hypothesis is that our mean is going to be equal to 30 hours. Our alternative, again, the company states that we want to see if they last longer than average. So our alternative hypothesis is that our mean is greater than 30. So for random, it is stated we take an SRS. For independent, 30 has to be less than or equal to 10% of all AAA batteries. And they make at least 300 of those. And then normal, 30 is greater than or equal to 30. So we're good there. So now for my t-test statistic, my x bar is 33.9 minus 30 all over my sample standard deviation, 9.8 over the square root of n, which is also 30. So this gives me a test statistic of 2.18. So now we're going to go to t-CDF on our calculator instead of normal CDF. And we need a lower and upper, and we just need degrees of freedom. So my lower bound, because my alternative is greater than, my lower bound is 2.18. My mean is 1E99. And then my degrees of freedom is 29 because my sample size is 30. And we are going to get a probability of 0.0188. So for our sentence, we can say, now we're going to compare that to our alpha, sorry. So our p-value is 0.0188, which is greater than alpha, which is 0.01. So in this case, we are going to fail to reject our null hypothesis. So our sentence, it says, there is not enough evidence to show that the mean battery life exceeds 30 hours. The next thing I want to show you is how to perform this test using your calculator. So there is a calculator function for a significance test for a mean, just like there were for proportions. So you go to stat and you go to tests. And then you want to do a t-test, which is number 2, which is t-test. Number 1 is z-test, but in this case we want a t-test, which is number 2. And then you have to decide between data or stats. So data means you've plugged something into the list feature of your calculator, which we didn't do here, so we want stats. So then you'll plug in your mu naught, which in this case is 30. Then your x bar, which is 33.9. Your sample standard deviation, which is 9.8. Your sample size n, which is 30, and then you choose your alternative hypothesis, which in this case is greater than mu naught. And then you hit calculate. So it will give you your t-test statistic, which is 2.18, which is what we got. It gives you the p-value, which is 0.0188, which is exactly what we got. And then it just repeats your x bar, your sample standard deviation, and your n. So you can get the exact same conclusion, because it's still greater than alpha, by using the calculator. So for our next example, we're going to go ahead and do one where we are given our data ahead of time. So we have the level of dissolved oxygen, which we'll abbreviate DO, in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the DO level at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. A dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. Do we have convincing evidence at the alpha equals 0.05 significance level that aquatic life in this stream is at risk? So first I want to decide between a t-test and a z-test. Obviously, if I'm given a list of sample data, I am going to be performing a t-test. So my null hypothesis, we know that the mean level of dissolved oxygen has to be 5 milligrams per liter. Our alternative in this case is we'll be looking to see if the mean is less than 5, because then it wouldn't be able to support aquatic life. Now we're going to check our conditions. So for random, we did select, or the person selected, random locations. Right. For independent here, you're going to want to treat this kind of like an experiment. Each location is going to be independent from the previous location. So it's not necessarily that 15 is less than or equal to 0.10 of all locations along the stream, because there's an infinite number of locations. It's just each location, its dissolved oxygen level is independent of whatever the previous locations were. And then normal. So I don't have the necessary sample size here because we only have a sample size of 15. So what I want to do is I want to check the graph. And the way we're going to check the graph is we're going to go into stat and then edit, and we're actually going to put our data into our list 1. So we'll start with 4.59, 5.04, 3.29, 5.23, 4.13, 5.5, 4.83, 4.4, 5.42, 6.38, 4.01, 4.66, 2.87, 5.73, and then 5.55. And now we want to graph. So you have choices in the graph. You can do a histogram, you can do a box plot. So we'll go to second y equals. We'll make sure our stat plot is on. I'm going to go ahead and I'm going to do a histogram. So, and then I go, once you select, you hit zoom and then 9. And then it's going to go ahead and graph your histogram. So I want something that looks approximately normal. And that's what we're going to get here. So for our normal here, we'll put graph is normal. I also need to go ahead and calculate my sample mean and my sample standard deviation because they weren't given to me. And since I've already input my data into list 1, I can go to stat and then calc and then one variable stats. And that will go ahead and calculate my mean and standard deviation for me. So we're going to get an X bar of 4.78 and a standard deviation of 0.9386. So when I calculate my test statistic T, we're going to take our mean, 4.78 minus 5, divided by our sample standard deviation, 0.9386, over the square root of 15, and we're going to get negative 0.93. So when I go to TCDF in the calculator, my lower bound is negative 1E99. Upper bound is negative 0.93. And then our degrees of freedom are 14. And that is going to give us our p-value of 0.1848. Which we're now going to compare to alpha. So our p-value is greater than our alpha of 0.05, which means we are going to fail to reject our null hypothesis, which tells us there is not enough evidence to show aquatic life is at risk. I do want to briefly talk about how I could have used my t-test to do this problem, because on a problem like this, where you're given the list of data, it's better to use your t-test in your calculator than it is to actually calculate your test statistic and to do TCDF. And that's for two reasons. One, we didn't have an exact mean here. So our mean was not exactly 4.78. We also didn't have an exact standard deviation. So I had to round for mean and standard deviation. And then when I calculated my test statistic, I had to round there as well. So I rounded a lot in this problem to find my p-value. So in this case, it's better to use the t-test on the calculator. And in this case, for your input, you would do data. So the only thing you need to plug in is your mu naught, which is 5. Your list should be from list 1, and then your alternative hypothesis, which would have been less than. And then you hit calculate. So thankfully, our t-test statistic is still negative 0.93, and our p-value is 0.1848. So it doesn't actually change our test statistic or our p-value. But on some occasions, the p-value might be slightly different. Again, not different enough that it should change your conclusion. You should still fail to reject no matter which method you choose. It's just that your p-value might be slightly different depending on which method you choose to do. All right, so the last thing we want to talk about is our type 1 and type 2 errors. So type 1 and type 2 errors work the same way for significance tests for means as they do for proportions. So they don't change. So in this case, type 1 error is still rejecting the null hypothesis when you should have failed to reject. So in this case, you would determine aquatic life is at risk. When it really isn't. So a consequence of this is that you provide help that isn't needed. So you do something to the water, you treat it to help lower the level of help raise the level of dissolved oxygen and unnecessarily. A type 2 error in this case would be determining aquatic life isn't at risk when it is. And a consequence of that would be not providing necessary help. Now in this case, the error that we could have made because we failed to reject, we determined aquatic life wasn't at risk, we could have performed a type 2 error here. Now, is it likely? Not really. Our p-value is 0.1848, and considering the highest level of alpha we'll typically use is 0.10, even if I raised my level of significance, I still would have failed to reject. So it's not as likely that we committed a type 2 error here. But if my p-value had been smaller, such as like 0.06, it could be possible, since it's still greater than 0.05, but if I had increased my alpha to 0.10, I would have rejected. So sometimes the likelihood of you committing that error, you really want to look at your p-value and see, well, if I had changed my alpha to a higher or lower level of significance, would I have come to the same conclusion? So let me know if you have any questions about performing a significance test for means.